This video shows what we're trying to build here, and it's an engine simulation. This should be the final result. This is a graph of engine RPM on the vertical axis and time in seconds on the horizontal axis. There are two buttons here. This turns the fuel on, that turns the fuel off completely. The RPM is being shown in the box here. The engine being modelled is shown in this system diagram. It's very, very simple. We have fuel variable F shown on the left hand side, which can be between 0 and 100%. The fuel then is burnt and produces a torque in the engine. So K1 is really the combustion process, simplified to just be a constant. So the torque is proportional to the fuel, or the torque is proportional to the actual fuel percentage. So 100% fuel will give you maximum torque. We then have the engine here. This is the inertia. J is the inertia in kilogram meter squared. Omega dot is the engine acceleration in radians per second squared. Omega is the speed of the engine in radians per second. So to go from acceleration to velocity, we simply integrate. To actually calculate the acceleration, you need to divide the net torque, that's Tn, the net torque by the inertia. Similar to F equals ma, but this is torque equals J omega dot. So the acceleration then is equal to the torque, net torque divided by J. This other box down here shows the friction torque. Tf is the friction, and the friction is subtracted from the combustion torque to give the net torque. The friction torque, we've assumed, is just a constant times the engine speed squared. That's what these two brackets mean. So it's a constant times omega squared. Whatever goes into that box on the arrow is squared times by k, and that will give you the value of Tf. And then S on the right hand side in RPM is simply converting from radians per second to revolutions per minute, multiplied by 60 and divided by 2 pi. These are the constants we're using in this simple demo. And we'll have to change those later depending on engine type or whatever. The code then to implement this block diagram, this is what we want to try and get. We want to try and get a real-time plot of engine speed against time. The code then to implement this block diagram is here. So you'll start with your basic empty file, and then just fill it in so it looks like this. I'll just quickly take you through here. dt is the time interval, so we're working in 0.05 seconds, that's 50 milliseconds. So this will actually run, this loop here will run 20 times per second. The variable W, omega, is engine speed. Omega dot is acceleration, F is the fuel as a percentage, J is the inertia, K1 is the combustion constant, K2 is the friction constant, T, Tn and Tf are all the torques, S is the initial speed in RPM, and X, this is the we're going to use this for the graphing. X is the distance along here, distance along the x-axis on the graph. So we start off, we've got two functions here, one is called start and the other one is called loop, and my web page should show both of them if I have to move this up a bit. So start happens once, we go in here, we draw a few rectangles on, and then that exits, and then the loop runs, and this runs every 50 milliseconds. And you'll probably notice that the key bits of information are here in these 7 lines. That's doing the mathematical modelling. The line below that, fill rectangle yellow, is just plotting a 2x2 dot on the graph at that x coordinate and that y coordinate. So that plots the graph by just doing lots of dots. Every time it goes around the loop, it will plot the engine speed s against x. There are two things here. This is the button. If the button is clicked, it checks to see if that button is clicked in that rectangle, and if it is, it puts the fuel at 100%. If this button is clicked, i.e. defined by that rectangle, it puts the fuel at 0. And then down here, we're just printing out some engine speed information, so we can know what's going on. You can print out lots more just by adding extra lines. Now in here, torque is equal to K1 times F. Where did that come from? Well, torque here is equal to K1 times F. Next line, TF is equal to K2 times math power W2, so omega squared, that is. TF is K2 times omega squared, and TF, here we are, look, is K2 times omega squared. Next line, Tn is equal to T take away Tf. That's the net torque is equal to the combustion torque take away the friction torque. Where did that come from? Let's have a look back at the diagram. Here we are, net torque is equal to combustion torque take away the friction torque. Next line, omega dot equals Tn divided by J. This is simply saying that the acceleration, angular acceleration, is equal to torque divided by moment of inertia. So, similar to F equals ma, acceleration equals the force divided by mass. Here, angular acceleration is equal to torque divided by inertia. And where did that come from in the diagram? Here we are, look, omega dot is equal to torque times 1 over J, which is the same as torque divided by inertia. Next line, omega equals omega plus omega dot times delta T. What is this? This is simply integration. And if this is digital integration, the new value of speed, or the new value of radians per second, equals the previous value of radians per second plus the acceleration in between times the time interval between these two values. So this is the one on the left hand side is the new value of W, and that's the old value of W. And remember, this is running every 50 milliseconds. Then we have speed equals, this is the RPM, is equal to the radians per second times 60 divided by 2 pi. Keep these in brackets, otherwise it'll start multiplying by pi and you want it to divide by pi. And then the last bit, x equals x plus 0.5. This is simply for plotting purposes. X is the horizontal coordinate on the graph, and here is x. If you wanted to speed up the graph, you'd have x plus 1. If you want to slow it down, you'd have x plus 0.25 or whatever you want. The rest of it you should be able to deduce.